want to try and get as far as we can. So, welcome everyone. We're going to do a little bit more vocab building today. A couple reasons behind the why for that. Where we were talking about ductility and what that means relative to plastic tensile strain. So elastic is the straight slope portion, and then plastic is this deformation region. So something that is highly ductile has a larger percent elongation. So it takes more and more and more and more and more energy and moves significantly. It stretches. So this is what we would think of as something that is, quote, softer steel, and, quote, harder steel would have a smaller percent of elongation. So they used to make everything out of the softer, cheaper grades of steel. It was easier to work with. It was cheaper to manufacture. Now the vehicles, especially in the truck region, there are actually some reasons why they are costing absolutely ludicrous numbers. Used to be in my lifetime, and I'm not exactly 158 years old, you could get a decent truck any day of the week for $5,000. That was not very long ago. Yet somebody calculates 3% inflation, like what, per hour? Yeah, okay. Being able to do math and understand how to use equations turns out to be pretty important. So we'll get to true stress and true strain and some of those other parameters a little bit later. But we want to understand a couple of things. So there's a couple different ratios, and the change in length with respect to the original length times 100 to give us a percent. Most steels are, at least mild steels, can stretch elastically somewhere on the order of like up to about 1% at the most before they become before they start plastic deformation. Another ductility measurement is based on percent reduction of area. That's what the percent RA means. So percent reduction of area. That means the original area minus the final area. So the final area after the necking begins, right before fracture, or right at the time of fracture, divided by the original, because that's your ending final area. So your cross section narrows. Because of that, there's a couple concepts that need to be understood. So the best way to think about this is we don't have a really good understanding of toughness exactly. So the energy that's needed to break a unit volume of material. You guys saw in the example of the magnesium forging video, you will remember that the magnesium had a tendency to fracture at when it was impacted. The magnesium had a tendency to fracture, and it was always along the diagonal planes. Because of the specific bond energies involved, and because of the way that those bonds are arranged, the way the atoms themselves are arranged in that face-centered cubic arrangement, it is very strong, but it tends to have 111 planes. And once you do hit that, it tends to have brittle fracture. And so it's very hard. And that's where a magnesium material is going to be more like the one on the left here, whereas the mild steel that that the same kid is normally using for forging is going to be more like this. So somewhere in between the two is going to be a higher carbon steel, something used for forging tools and all sorts of things like that. So it's going to be somewhere sort of up in between these and have a narrower curve or something like that. Polymers are very, very low, generally speaking, in terms of toughness. you would disagree with that statement if you had been bashed over the head with a 1.5 inch diameter Delrin rod, for instance. Um, uh, the of the polymers, that's one of the tougher ones, and it's why we do a lot of prototyping and building in Delrin, because it's a little cheaper. But yeah, maybe Tyler, you can chime in, yes or no, and why, as to whether or not you'd want to be hit with a 1.5 inch dowel with Delrin, because you've actually, I think you guys worked with it in the shop a number of times, right? Yes, it does make very good bearings. Delrin has a very low change in dimensional. Oh, that's, yeah, speaker's not working. That's not helpful. That's okay. Yeah, technology. All, just remember how much better online education was going to be. Doing our best here, folks. Not much we can do about it. Well, there are some things that could be done about it, but they won't, so it doesn't really matter. There's no point in discussing it. So there are a couple things that could be done here. The the meaning for toughness is really important. It's the energy to break a unit volume of material. So you watched as those pieces were sheared off in diagonals as the magnesium was being pounded by the forging hammer. And it was really tough and didn't want to move. That doesn't necessarily mean that it was an extremely tough material, though, because of the definition of toughness. So it's actually not a tough material. It's more ceramic-like, which means it has a small toughness rather than a large toughness, like a steel would in comparison. So steel, the reason why we make hammers out of steel is because you can hammer them repeatedly without them, typically speaking, just shattering or doing all sorts of terrible things. The reason we use that material is it turns out that's one of the largest toughnesses, is the grade of steel that's typically used in hammers. So there's a lot of things that we understand as a result of that process. Polymers, by contrast, are very, very far to the low end. So the things that have small toughness are often a very narrow elastic region, so not very much change, compared to almost double that for tougher material. But that's the strain side. They can take a lot less stress overall, but this is why an aircraft frame, for instance, is more like the one on the left here, where we have a little bit more in the way of like a high tensile strength aluminum, something like a 7075 aluminum or something like that, right? What that's going to do is that's going to take load, and then suddenly and explosively break apart. So all of the sudden, uh, uh, fighter, for instance, a fighter jet is a good example of extremely high G forces being applied. You have wind resistance and all sorts of things coming into play. So those frames take a very high degree of stress. So all of a sudden they go into a very sharp maneuver from a very high rate of speed. That large directional change becomes that's a very high stress situation. And what that ultimately means is for the material, it's going to take stress, and then break catastrophically right here. That means that suddenly the wing is no longer attached to the aircraft or something like that. There's a lot of videos of airframes failing under load like that. And those are things that happen because of the information that is on this graph. So that's another key piece of this puzzle. A ductile fracture is a combination of the elastic and the plastic energy. And you can think of that as the energy being stored as you stretch the material farther and farther and farther. you're filling up this area with more and more and more and more energy. So it's an energy because it's the integral of the stress strain curve. So all the area under the curve is what tells us the information that we need. This is important for a range of reasons. And I'm going to go to this to give another, to help kind of fill this out a little bit.
Closer look at strength, ductility, and toughness, 3 very important material properties. Let's get started. Strength is a measure of the stress a material can withstand. 2 different values are typically used to define the strength of a material, the ultimate strength and the yield strength. Let's define them by taking a look at the stress-strain curve obtained from a tensile test. The ultimate tensile strength of a material is defined as the maximum stress, which is reached during the tensile test, corresponding to this point on the stress-strain curve. It is the maximum stress the material can withstand during a tensile test. The yield strength is defined as the stress at which a material begins to deform plastically. Stressing a material beyond its yield strength will result in permanent deformation after the load is removed. Many structures and components are designed to ensure that they only deform elastically. This makes the yield strength a commonly used criterion for defining failure in engineering design codes. It is possible for failure to occur at stress levels well below the yield strength, if the applied load varies with time. This failure mode is called fatigue, and I will cover it in a separate video. For some materials, the transition from elastic to plastic deformation is not clearly defined. In these cases, the yield strength can be defined using the 0.2% offset method. This involves drawing a line with the slope equal to Young's modulus and shifting it 0.2% to the right on the stress-strain curve. So far, we have only discussed strengths in the tensile direction. But what about the compressive direction? For ductile materials like mild steel, the yield and ultimate strengths are very similar in the tensile and the compressive directions. Tensile tests are usually easier to carry out than compression tests, and so compression tests aren't often performed for these materials. For brittle materials like concrete and ceramics, however, the material strength is much larger in compression than in tension. I will talk about why this is the case later on in the video. First, let's look at some examples of strength values for a few different materials. Tensile yield strengths are shown for ductile materials, and ultimate compressive strengths are shown for brittle materials. Graphene is the strongest material to have ever been tested. It is a 2-dimensional material made up of a single layer of carbon atoms arranged in a hexagonal lattice and linked by strong covalent bonds. Defect-free graphene has an ultimate tensile strength of up to 130 gigapascals, or 19,000 ksi. I've mentioned material ductility a few times in this video, so now is probably a good time to define it properly. Ductility is a measure of the ability of a material to deform plastically before fracture. Let's return to our stress-strain curve. Materials which undergo large amounts of plastic deformation before they break are called ductile materials. These materials fracture at very large strains. Mild steel and gold are examples of very ductile materials. Materials which fracture at very low strains with little to no plastic deformation are said to be brittle. Glass and ceramics like porcelain are examples of brittle materials. Because they don't deform plastically, the concept of yield strength is irrelevant for brittle materials. There is no defined transition point between ductile and brittle behavior. Typically, a material which has a strain at fracture of less than 5% is considered to be brittle. Now that we have covered what ductile and brittle materials are, let's return to the question of why brittle materials are much stronger in compression than in tension. There are two factors at play. The first factor is that tensile loads tend to encourage the formation and propagation of cracks, whereas compressive loads do not, as illustrated here. The second factor is that in brittle materials, very little or no plastic deformation occurs to redistribute stresses at existing flaws. This means that large stress concentrations build up at the crack tip, resulting in fracture. In ductile materials, plastic deformation occurs, which relieves these localized stresses. Ductility can be dependent on temperature. A lot of different types of steel, for example, are ductile at room temperature, but become brittle when the temperature drops to below the ductile to brittle transition temperature. This transition temperature is an important design consideration, because ductile failure is normally preferred to brittle failure. One very famous example of brittle failure is the Titanic. The icy waters of the North Atlantic are thought to have caused the steel of the ship's hull to drop below its ductile to brittle transition temperature, resulting in catastrophic brittle fracture. Toughness is the ability of a material to absorb energy up the fracture. It can be calculated as the area under the stress-strain curve. If the area under the stress-strain curve is large, the material will have high toughness, and so will be able to absorb a large amount of energy before fracturing. For a material to have high toughness, it should have a good balance of both ductility and strength. Low-strength materials and brittle materials tend to have low toughness. A related property is resilience, which is the ability of a material to absorb energy when deforming elastically. It corresponds to the area under the stress-strain curve, but only within the elastic region. Materials with high resilience are well suited for applications where plastic deformation is to be avoided. To summarize, the yield strength of a material defines the stress at which it begins to deform plastically. The ultimate tensile strength defines the maximum stress which is reached during the tensile test. Ductility is a measure of the ability of a material to deform plastically. Toughness is a measure of the ability of a material to absorb energy up until fracture. And resilience is a measure of the ability of a material to absorb energy while deforming elastically. That's it for now. If you enjoyed the video, please remember to subscribe.
There's a couple pieces there that are key, a couple concepts that are key there. But first, we need to start by completely ruining what little of your childhood is left. In the comments below, explain why the material used in a certain famous video game is good or terrible as an idea. If you were to make armor and a sword out of diamond, is that in fact a good material or a terrible material, and why, based on the terms that you have now learned? I'm curious to see what the results look like. Think about how these terms interact, because we have to have toughness, brittle, ductility, all of those factors. Is that a good idea or bad idea? And why? I'm familiar with the diamond armor being presented as pretty good. However, um, I'm curious to see if you guys can defend whether or not it would be a good material based on let's see. Let's see. Um, a couple people have done a version of it. Let's see. Uh, there are a couple examples of this. Let's see. There are, I know there was an actual materials test of one, trying to see if I can actually find it. There's a lot of examples of those. Let me see if I can find it. Because what I want you guys to do is be able to clearly articulate why this is or is not the case. Um, all right, let's see. So there is actually at least one person who has the full scale credibility based on facial hair alone to be able to answer this question. Okay, we got a few more answers in. Um, strong, tough, heavy, too expensive, good. Those are reasons for manufacturing problems. Not malleable. Yeah, it turns out if you try to forge diamond, that doesn't exactly work. Good. It's too brittle. The Aztec obsidian swords, right? Yes. There's a couple points that this particular video will touch on that'll help to clarify some of that. Yes, not a good idea because of its brittle transition. Its resistance to impact is terrible, and that's the key aspect. So, diamond being a ceramic, there's one more thing that I want to uh, use as a reference point. Um, so there's one more piece I want to incorporate. Um, there is a YouTube scientist, um, assuming we can call him that, uh, who has done some very important work. I'm going to get it up to the point of relevance here. Um, So this is the relevant point here. Understanding the full depth and breadth of science and what the difference is between ultimate strength and toughness is important. So yeah, no, we've got to make sure that these guys are included. I mean, they're wearing lab coats.
Tape is racist.
But talk is cheap ammunition is what, Charlie?
Provided by.
I don't know. I don't know what else we expected to happen.
Ungovernable task
it would have been
force.
fine. Well, I mean, that armor doesn't look too bad. I mean, no, it's not.
Completely and utterly shattered. And they decide, I know, if one is not adequate, then clearly more is better.
Therefore, 50 is just 0.50. That's way more. Therefore, 3 plates. No way. That totally stopped it, dude. Dude, has Call of Duty ever lied? Okay, well, 50's on the line. I said third plate. Hold on, is this the...
That's from before.
That's the old one.
This is the bicycle tire.
Oh, look at that. Hold on.
Third plate. That's what Micah said.
Well, we can just count how many it went through, and that's...
Yeah, okay. We have 1, 2, 3.
So the ductile versus brittle argument depends on what the application is. Brittle is great for one good impact, and then it's completely destroyed. So this guy has full credibility on details of whether or not diamond would be an adequate material, and this is some of the reasoning why he actually gets into the properties, and based purely on, again, the facial hair alone. Dude has full credibility when talking about swords. So there's that.
Do you like my sword, my diamond sword?
No. People still ask about this, and I realized I've never actually made a video about it, so here we go. Would a sword made of diamond be any good? Short answer, no. Long answer, no. I've made that joke before. Here is the long answer. So first off, what is diamond? Diamond is a solid form of carbon with crystalline atomic structure. It has the highest number of atoms per volume, and its atomic bonds are remarkably strong, which makes it the hardest and least compressible material, but also inflexible and brittle. The bonds between atoms are so strong, it doesn't allow much deformation. If you try to put a dent in diamond, it's practically impossible. Whereas steel can also resist deformation, but it's not as stiff and capable of elastic deformation, which means the ability of the material to change its shape temporarily and then return to its original shape. What diamond lacks is toughness, the ability to resist cracking and fracturing, whereas steel has plenty. Of course, steel can crack and fracture too, but it takes quite a lot of impact force for that to happen. If you made the exact same sword blade of steel and diamond, assuming a world where steel and diamond cost the same, shall we say, and then you struck one with the other, the steel blade would probably be damaged, but it would be in one piece, whereas the diamond blade would shatter. Bronze goes in the opposite direction. It lacks hardness, but it's got plenty of toughness. So on impact, this is very unlikely to break, but it's more likely to bend and then stay deformed, which also means that the edge can roll and otherwise deform. It's not as likely to chip. If you were to keep bending this repeatedly, so bend it, bend, straighten, at the point where it bends, you would basically be work hardening it, so then it's more likely to break, but otherwise, not so much. And of course, with a steel sword, it depends a lot on how it's heat treated and tempered. You can make steel extremely hard, but then it becomes brittle, or you can make it fairly soft. If you compare mild steel, for example, to high carbon steel, let's say with a particularly high carbon content, say 1095 high carbon steel, the latter is much more likely to break, but unlikely to deform permanently, whereas mild steel will deform permanently rather easily, not as easy to break. You get the idea. If we look at a katana blade, which is traditionally differentially hardened, you have a harder edge and a softer spine. So the idea is the hard edge will retain the sharpness for longer and is more resistant to abrasion and wear, while the spine allows it to deform without breaking. Whereas if you have a monosteel blade, where the hardness and toughness is basically in between the edge and the spine of a katana, roughly, there's plenty of variation. But now it may deform, so the edge may roll or otherwise permanently deform. It may chip, the entire blade may bend a little bit, or it may break. but either is not as likely. Basically, the difference between min-maxing versus a more balanced build. Both have their pros and cons, obviously. So what about diamond? Is there a way to make this work, potentially? Just like a differentially hardened katana blade, you could combine two different materials in an attempt to compensate for each other's weakness. One historical example of that being done is the Aztec Maquahuit, which was a wooden core with obsidian blades. I have one that I was supposed to test, and I did test it, but it didn't turn out so well. Yikes, the bottle is too much. Okay, yeah, there's one here. Yeah. One there.
Did something on the opposite side fall off too?
Yeah. Apparently because the pitch used to glue these blades ended up too brittle, ironically. So these kept breaking off, falling off, and you can make that better, depending on the composition of the glue, you can optimize that. But always the problem is that the obsidian blades, again, just like diamond, are hard but very brittle. In fact, the extreme sharpness that obsidian is famous for is also its downfall. What makes it so sharp is that it fractures into an extremely thin feather edge. And that will, of course, part material more effectively. The thinner it is, the more effective it is. But that also means you have very little material all the way at the end, because it becomes so thin and is also brittle, it will just crumble on impact. So basically you have that extreme sharpness, the maximum sharpness you have for one cut. On the first impact, much of that feather edge is already going to crumble. It's kind of a disposable weapon. And in fact, that's part of what makes this so horrible, the fact that obsidian will shatter and remain in the wound.
At Mint Mobile, we like to do the opposite of what Big Wireless does. They charge you a lot, we charge you a little.
The Maquahuit is commonly interpreted as a non-metal sword, but I see it really more as an enhanced club. It's really more of an impact device that has the very nasty side effect of cutting into flesh and probably leaving fragments of obsidian inside of the wound. It's worth pointing out that depending on the design, it may look more sword-like or more like a club. And of course, there were other Aztec weapons that were in fact war clubs or spear-like. Now, it also depends on how you make it. If instead of using that feather edge, you chip or maybe even grind an edge, it's not going to be as crazy sharp. It doesn't thin out as much, but it's going to be more durable. You can sacrifice some sharpness for durability. It also makes quite a difference how you shape that core. This one here has hard 90-degree corners. The problem with that is, as the blades cut into the material, the blades taper naturally, but eventually this hard corner here is going to hit the target and it's going to stop there. It's not as likely to enter the target because suddenly you have a hard shoulder there that impacts, and that's not likely to stop the cut. If you taper it, you have a better chance of penetrating, and I'm assuming that's what they generally did. So my point in talking so much about the Maquahuit is you could do the exact same thing with diamond. It's a pretty similar material, at least in terms of hardness and lack of toughness. There's something called polycrystalline diamond, or PCD, which is made through a process called sintering, which fuses diamond crystals with a metallic binder like tungsten and cobalt. That method alleviates some of the brittleness of natural diamond. It's still fairly brittle compared to something like steel, but not quite as much so. The problem is diamond is even more brittle than obsidian, correct me if I'm wrong. I'm not sure where polycrystalline diamond ranks. It's less brittle than natural diamond. I don't know how it compares to obsidian, but either way, it's conceivable that you could make something like, say, a polypropylene core, be it a Maquahuit or some kind of sword design with maybe polycrystalline diamond edge laid into it. So that edge could still, of course, chip or crack or otherwise be damaged on impact. But the advantage would be excellent edge retention. It would stay sharp for very long with a lot of use, so you wouldn't have to resharpen it much, if at all. Of course, it also depends on how the diamond is processed and shaped and all that, but it could be possible in, say, a fantasy world where diamond doesn't have this artificially inflated price as it has in our economy. But a blade made entirely of diamond, or crystal for that matter, as cool as it would be, doesn't work in the real world. You would need magic for that. Anyway, hope you found this interesting. Thanks for watching, and have a good one.
So again, sorry to break all of your childhoods, but has to be done. We have to understand the realities and cost trade of materials. So it's important to have real credible scientists helping us with the information, as always. This is something that goes hand in hand. This is a definition called resilience. So this is the ability of a material to store energy. So we talked about the toughness being how much total energy can the material absorb for a unit volume. This is the energy that is able to be stored and then released elastically. So spring steels have a much higher resilience than the other materials. That's why I said today is very much all vocab, but it's vocab that's based on mathematical necessities of the material. So there are real limitations to what these things can do, and there's real limitations to how far they can go. But we have the ability of a material to store some amount of energy in that elastic region, and that is the integral below that up until from 0 to epsilon y, the yield strain. So the strain at which yield begins and the stress at which, that's the stress and strain at which yield begins on the stress strain curve. And we can simplify that down to half of the multiple between those two, between sigma y and epsilon y is our approximate resilience UR. So the more resilience a material has, the lesser the slope of that stress strain curve. So something like certain polymers can be actually quite resilient, and that's why they make good elastomers, because they can store elastic strain very well. So the elastic strain recovery, we've talked about the process, so this will look a little bit familiar, but it looks like you load the material, you unload the material, it comes back with the same slope because it's a mathematical necessity based on the Young's modulus, right? So this is a thing that we know. There is an elastic strain recovery that is the same. You load again, you come to a new yield point, and there's some additional plastic strain applied. So the more times you do that, the closer you get to fatiguing the metal. And fatigue just corresponds with the degree to which the material can handle being repeatedly stressed and unloaded, stressed and unloaded, stressed and unloaded. So fatigue happens when enough damage has been done, enough strain has built up in the material to where it can no longer return elastically. There's too much plastic deformation that has happened. So that's when the soda tab finally breaks off. You've stored enough energy in that system that it can no longer elastically recover. The plastic deformation takes over and you get cracking. That concept is also why, because of the stresses that concentrate at the tip of a crack in a brittle material, this is why you'll hear, especially folks that have done a lot of repair on farm equipment, for instance. Let me see in the comments, anyone have a family member at one point in time that has told them to drill a hole ahead of a crack in some material, piece of equipment, a lawnmower deck, or whatever? Has anyone actually heard those words said, or have you guys entirely grown up actually on social media and never actually seen the sun or touched grass? I don't even know if you've been given that advice, Tyler. A lot of people would say just weld it, but I'm wondering if anyone has actually ever been told, or is it just me? Type no if you have no idea what I'm talking about. I don't see answers rolling in. So I'm going to go with maybe nobody has actually heard that advice before. The reason for drilling a hole at the head of a crack is in order to stop the fault propagation. So the stress will be concentrated all the way up until the crack runs into the new hole that's drilled, and then it can't continue to run. So a hole is there to be able to stop the stress from continuing to run through the material. So the crack will stop when you drill a hole at the head of the crack. It's counterintuitive, but it's actually the same thing that they do basically with high-end sophisticated windshield chip repair is remove a bunch of the loose debris and then backfill everything using a vacuum to replace all of the air with resin that helps to rebind everything. It's the same kind of idea. So it's all about brittle fracture and stopping that cracking from happening. That's because the material has a large hardness, which is what we're talking about here, and that's why I wanted to bring that up. The hardness is the resistance to indentation on the surface. So the hardness is not the same thing as the sharpness of a material. They are very, very different properties. The hardness helps to maintain sharpness for longer. Less hardness maintains that sharpness for not as long. And that's the way that these things are related. You're going to do some experiments where you're actually going to be doing indentation. We're not going to be using 10 millimeter spheres. I think ours on the new equipment are a little smaller. I can't remember offhand, but those might be about 3 millimeter, 2.5, something like that. They're a little bit smaller, I think, on the newer machines. Used to be, we had about a 6 millimeter or so, 5 or 6 millimeter, something like that, on some of the old machines, but I think those are all moved out to other locations now. So the hardness is the resisting to indentation on the surface. So how hard is the actual surface itself? This gives better wear properties. So this is a good example of, in the case of something like a material that has to have a lot of rotation and stresses present. So in the case of something like bearing surfaces, this is very, very important. So you need something that has a fairly high hardness. In the case of what Tyler was referencing, for instance, the Delrin being good for bushing materials for the race car. The Delrin, what that does is that acts as, at least relative to polymers, a very high hardness surface, meaning that it's very good for wear application. So it is more like working with wood than it is like working with a much more pliable plastic material. So some plastics are almost like machining a bar of soap. It's not really resistant. It's very easy to work with. This is why 3D printing of some of these materials is so simple and easy, because they're very compliant, especially at temperature. They become a lot less compliant if it's something like Delrin. So you're not going to see a lot of 3D printers that could do something like use a Delrin filament, assuming you could get Delrin to cooperate as a filament, which would be a separate problem. So you apply a force across the material, across this indenter. You make an indentation that has a diameter. You measure the approximate diameter of the material, and you can get the mean hardness. The new machines that we have do some of this work for you and get a sense of what the indentation sizes are. But you're still going to do some hand measurements to verify some of that in the labs that you're doing. Then you're going to see what the materials look like after they have been heat treated. So the plastics are going to be very low on this end. Brasses and aluminum alloys are actually quite a bit harder. So there's a reason why we use brass for something like keys. Turns out plastic is a terrible material for making keys out of. Machinable steels, so mild steels or annealed steels, are a lot lower. Files are harder than the annealed and low carbon steels, because files have to cut into those surfaces, but files themselves are not actually all that hard compared to some of the cutting tools. And then nitrided steels, these become the very, very expensive cutting bits. And then there's some of this diamond materials, diamond tools and tooling and things, that become, those are usually the industrial grade diamonds. Those are going to be at the highest end of hardness. So there's a lot of interesting grades in between here, but something like a file is going to do much smaller indentation than something like a brass or aluminum alloy. Copper is somewhere in here too. I think it's I want to say it's a little softer than brass, but sort of closer to the aluminum. So it's still in this same range. It's a relatively soft metal overall, but nowhere near as hard as like a good grade of cutting tool. So especially like cobalt tools, I think fall somewhere in this range. Truly nitride coated steels are even harder still. So there's a range of properties there. There's a couple different scales, and by a couple, I mean there's actually a lot. There's really two that'll be the focus, at least as far as this text is concerned. Rockwell. So there's no major sample damage, and the scale runs to 130, but the really useful range is the 20 to 100. The minor load at 10 kilograms versus the major load at 60, and you'll see grades Rockwell A, B, and C, 150 kilograms. So A is a diamond indenter, B is a 1/16 inch ball, and C is a diamond indenter. Why? Well, you'd have to ask Senor Rockwell as to why do diamond for two of them and not for the third one. It's because of, in certain cases, it's because of the kinds of materials that they started measuring, and yeah, there's a whole lot of additional history there. Brinell hardness. This is going to be real similar. So here's another interesting fact. Probably most of you use steel razors at some level. Does anyone know why, using the Brinell hardness as a reference, does anyone know why razors tend to be so quickly dulled? Because it seems like hair is really not all that bad. But does anyone know why, using these terms, the steel razors dull so quickly? Let's see. Nobody? Okay. It turns out that specifically facial hair has the approximate Brinell hardness of a copper wire of the same diameter. So there is a very real tendency there for the steel to be dulled. And there's a couple different scales that the Brinell hardness is done using. So the tensile strength is related to the Brinell hardness by a constant for PSI A, meaning absolute, for absolute PSI in terms of tensile strength. This is 500 times the Brinell hardness. So divide the absolute tensile strength in PSI by 500 to get the Brinell hardness, or in megapascals, it's divided by 3.45. So this is kind of an idea comparing some of the different indentation types. So there's Vickers, there's Knoop there's Rockwell and the superficial Rockwell. So the superficial Rockwell are, again, probably going to be these 16th diameter balls. The diamond cone indenter is more common for measuring most of the relevant Rockwell range. The superficial Rockwell is useful for things like polymers that don't have the same resistance. If you add 150 kilograms to a diamond indenter on a polymer, you're going to punch straight through all the way to the floor. So a lot of polymers, that's not a useful measurement. So the indenter type, and then what the angles are, what the surface contact looks like. A diamond pyramid with a different aspect ratio or an uneven aspect ratio is the Knoop hardness. And so there's a couple conversions where you can go kind of back and forth. But for the most part, we're going to focus on Rockwell and or Burnell hardness. So often, in the case of Burnell, you're using something like steel or tungsten carbide. I think the ones that we had used to be steel. So here's where we touch on the concepts of true stress and true strain. These are different from the engineering stress and engineering strain, because the engineering is what we're actually measuring, but keeping in mind that as the material is stretched, that surface area is reduced. So there's a couple of things that that are needed there in terms of understanding what's true. So the true stress is the force divided by the initial area rather than the force divided by the area that's in question. So the force divided by not the true, so it's not a naught, it's actually AI. So AI is at every point along the curve divided by the area as it's changing is the true stress. The true strain, similarly, is the log of the length at that point in time relative to the original length. So that this becomes the stress of 1 plus the strain, and the true strain is the log of 1 plus the strain. So this is what gives us our relationship to understand what's actually happening, because the stress that the material is taking on is actually much higher, since that area becomes much smaller. So the material continues to stress and stress and stress until it reaches a certain point, and then it breaks. There's just a difference in the way that it gets tested, because we see as that area decreases, the overall stress on the part drops off, but because that area is smaller, it's actually just concentrating until it fails. Hardening process does a couple of things. It increases the sigma Y. So it increases the yield stress because of plastic deformation. So there's a small amount of hardening here versus a large amount of hardening here. And there's a couple parameters here. I don't think we're actually going to use this very heavily in a lot of problems, but it's important for you to know that it exists. So the true stress is proportional to it's proportional to a number based on, it's a hardening exponent based on what material it is, and it varies. And epsilon t, so the true strain, meaning the natural log of the length relative to the original length, times our constant k that we've talked about a little bit previously. There's also a lot of variability in the materials properties. So if you test multiple samples, some of the samples could have flaws or defects. If, for instance, somebody dropped some of these materials on a workbench or the edge of something, or they slipped out of the vise and chipped one side somewhere in the middle, that creates a small defect that changes the critical properties, because that small defect could create a stress concentrator that that takes place. So you need to understand how to take some mean and standard deviation. Typically, that's not going to be something that you guys are hand calculating, but doing in a spreadsheet. But that's the formula for standard deviation for those of you that have not had a statistics course yet. It's the sum from 1 to n of the xi, so the value at each point, minus the average, the mean, the square of that, the sum of the squares of the differences there are the actual standard deviation, divided by n minus 1, which is a mathematical necessity because of having used up some of the information, one of the degrees of freedom to actually calculate the average, stuff that you guys will learn about in more detail in a different class. We also have safety factors that come in, and this is why I say this is literally like the everything in materials chapter, but you really can't separate it all out. All of this is important vocabulary to understand what to do with materials later. So the safety factors usually are denoted by N. So you do all of this careful work and make sure that everything is not going to break under the design stresses. Then they give you a safety factor of often somewhere between 2 and 4, really. So sometimes it's as low as 1.2. So basically you do all of that hard work and then say the actual working stress is the yield divided by often something like 3 in practice. So you multiply all of your beam thicknesses effectively by 3 at the end of the day. And that's how you try to not kill people. The factor of safety there is to try and make sure that you didn't screw up the calculation. It's really what that's for. There's other reasons behind that, but the factor of safety is important. So an example being something like calculate a diameter to ensure that the yield does not occur for the 1045 carbon steel rod with a factor of safety of 5. So we have a force. Maybe this is a rod that's attached to a catwalk high up in a building or something like that. So it's a 1045 plain carbon, so it's not really a high carbon steel. It's high enough that you could sort of do a little bit of hardening, kind of, but it's not going to have a huge effect. So our yield strength is 310 megapascals, and our tensile strength is 565 megapascals. So ultimate tensile strength is what that is. So the working stress is equivalent to the yield divided by N. So the yield divided by our 5, 310 divided by 5, our working stress is the 220,000 Newton. So 220 kilonewton divided by, this is why I say this is likely something like a catwalk or something that's holding a lot of force from a number of people across it. 220,000 newtons divided by pi times d, because it's the total area, d squared over 4. We solve for d and we get something like 6.7 centimeters. So this is the way that sizing of materials is done, is we need to size that beam and all of the other components around it, everything attached to it. We have to size using the same process. So you figure out what the actual dimensions of those are based on the actual factor of safety that needs to be included. So stress and strain are size independent measurements of the load and displacement. These are what we use in order to develop the stress strain curve so that we can understand what the elastic behavior is. The elastic is that reversible portion that we have a linear relationship, and it's usually related by the Young's modulus or the elastic modulus. The plastic behavior is the permanent deformation. So it's often tensile, sometimes compressive, but it's uniaxial, and it's stress that exceeds the yield stress, so sigma y. So toughness is the amount of energy needed to break a unit volume of material, and then ductility is the plastic strain at failure. So these are important terms to be able to understand how they all work together and what some of these do in order to cooperate. So we're about at that point now for questions. So what questions do you guys have? Let's first get let's first get a check-in. Yeah, 1/16 inch ball and dinner. Okay, that's what I thought was the case there. Yeah, you also want to watch out for there's a couple things that happen. So, okay, so some people have heard of that. That's good. All right, for whatever reason, comments were not coming through at my end. All right. So let's get a grand clarity scale check. Where are you guys at? Simple 1 to 10, 10 being our holy water standard and 1 being dry dirt. Where are we on the clarity scale?